When we think of crystals, our minds often wander to deep caves or molten magma. However, the world's oceans are teeming with crystals, and among them, Aragonite stands out as arguably the most significant crystal you've never heard of. Far more than just a pretty specimen in a rock collector's display, Aragonite plays a crucial role in marine ecosystems and provides invaluable insights into our planet's ancient oceans. Let's dive into the fascinating world of this unsung crystal hero. What is Aragonite? Aragonite is a form of calcium carbonate, CaCO3, with a specific crystal structure. It's one of the three naturally occurring polymorphs of calcium carbonate, alongside calcite and the rarer vaterite. The key difference between these forms lies in their crystal structure. Aragonite, orthorhombic crystal structure; calcite, trigonal crystal structure; vaterite, hexagonal-based prism structure, unstable in water. In the ocean, aragonite and calcite are the primary forms of calcium carbonate, with the prevalence of each depending on various environmental factors. The formation of aragonite in the ocean. The ocean is a complex soup of dissolved ions, including calcium, Ca2, and carbonate, CO3 When conditions are right, these ions combine to form calcium carbonate. Whether this calcium carbonate takes the form of aragonite or calcite largely depends on the concentration of dissolved magnesium in the water. Magnesium ions interfere with the formation of calcite crystals. Therefore, in waters with higher magnesium content, aragonite becomes the predominant form of calcium carbonate. This is why our current oceans are often referred to as aragonite seas. The biological importance of aragonite. Aragonite isn't just a passive participant in ocean chemistry. It's actively used by a wide variety of marine organisms. Mollusks, mussels, oysters, and sea snails use aragonite to form their protective shells. Corals. Reef-building corals incorporate aragonite into their skeletal structures. Certain seaweeds. Some species of seaweed use aragonite to build rigid skeletal structures. Beyond its structural uses, aragonite is also responsible for some of the ocean's most beautiful natural creations. Mother of pearl. The iridescent inner layer of many mollusk shells is composed of aragonite. Pearls. These precious gems are primarily made of aragonite. Ammonite. This rare iridescent gemstone is formed from fossilized aragonite in ammonite shells. Aragonite and beach formation. Many of the world's most beautiful white sandy beaches owe their existence to aragonite. However, the process of beach formation might surprise you. In places like Hawaii and the Caribbean, up to 70% of carbonate sand has passed through the digestive system of parrotfish. These fish feed on hard corals, crunching through the aragonite structures to reach the organic matter inside. The indigestible aragonite is then excreted as sand-sized particles, eventually forming those picturesque white beaches. The delicate balance. Aragonite and ocean acidity. The formation and stability of aragonite in the ocean is intricately linked to ocean acidity. As atmospheric carbon dioxide, CO2, dissolves in seawater, it forms carbonic acid, increasing the ocean's acidity. This poses a significant threat to aragonite-dependent organisms for two reasons. Carbonate depletion. The acid reacts with carbonate ions, reducing their availability for organisms to build their aragonite structures. Shell dissolution. Increased acidity can begin to dissolve existing aragonite structures, such as coral reefs and mollusk shells. This process, known as ocean acidification, is a major concern in the face of rising atmospheric CO2 levels due to human activities. Aragonite as a window to the past. One of the most fascinating aspects of aragonite is its ability to provide insights into Earth's ancient oceans. Geologists and paleoceanographers use the presence or absence of aragonite in fossil records to reconstruct past ocean conditions. The prevalence of aragonite versus calcite in the oceans has varied over geological time, primarily due to changes in ocean magnesium levels. These changes are largely driven by variations in seafloor spreading rates. High seafloor spreading rates. More volcanic rock is exposed to seawater, leading to increased magnesium levels and favoring aragonite formation. Low seafloor spreading rates. Less magnesium is released into the oceans, favoring calcite formation. This alternation between aragonite seas and calcite seas occurs over millions of years. For instance, about 70 million years ago, During the Cretaceous period, the oceans were calcite seas due to lower magnesium levels. By studying the crystal structure of fossilized marine organisms, scientists can determine whether they built their shells with aragonite or calcite. This information provides valuable clues about ocean chemistry, temperature, and even depth at the time these organisms lived. Other factors that influence aragonite formation and can be inferred from the fossil record include ocean temperature. Warmer waters tend to favor aragonite formation. Water depth. Aragonite is more stable at shallower depths due to pressure differences. CO2 levels. Higher atmospheric CO2 can lead to more acidic oceans, affecting aragonite formation. The future of aragonite in our oceans. As we face the challenges of climate change and ocean acidification, the future of aragonite in our oceans is a topic of significant concern. The ability of marine organisms to form aragonite structures is crucial for the health of ocean ecosystems, from the tiniest plankton to massive coral reefs. Monitoring aragonite saturation levels in the oceans has become an important part of assessing ocean health. Areas where aragonite is undersaturated are particularly concerning, as they can lead to the dissolution of existing aragonite structures and make it difficult for organisms to form new ones. Research into aragonite formation and its role in marine ecosystems continues to be vital for several reasons. Conservation. Understanding aragonite dynamics helps in developing strategies to protect vulnerable marine ecosystems, particularly coral reefs. Climate science. Aragonite formation and dissolution play a role in the ocean's carbon cycle, which is crucial for understanding and modeling climate change. Paleoclimatology. Studying aragonite in the fossil record helps reconstruct past climate conditions, providing context for current climate change. Biomimicry. The unique properties of biogenic aragonite structures, such as nacre mother of pearl, inspire materials scientists in developing new, strong, and lightweight materials. Conclusion. Aragonite, often overlooked in discussions of ocean chemistry and marine life, plays a pivotal role in shaping our ocean's past, present, and future. From the shells of tiny mollusks to vast coral reefs, from sandy beaches to the depths of geological time, aragonite's influence is far-reaching and profound. As we continue to explore and understand our oceans, aragonite serves as a crucial indicator of ocean health and a window into Earth's history. Its story intertwines with the broader narratives of climate change, ocean acidification, and the delicate balance of marine ecosystems. The next time you admire a seashell, walk on a white sandy beach, or hear about the plight of coral reefs, remember the humble aragonite crystal. In its delicate structure lies a wealth of information about our planet's oceans, past, present, and future. As we face the challenges of a changing climate, the story of aragonite reminds us of the intricate connections between geology, chemistry, and life in our blue planet's waters.